assume that Dirac was responsible for. Now we know, I think, everything we need to know about harmonic oscillators, at least for the moment. And that was just a mathematical interlude, if you like, so that we'd have it in front of us when we need it. Put it up on top. Any questions about harmonic oscillators or multiple harmonic oscillators? Oh, one thing. What happens, here's a particular vector or a particular state which has a certain set of occupation numbers. Let's hit it with a creation operator for the ith oscillator. We're going to the ith oscillator and we're applying 1 unit of creation to it, or 1 unit of elevation. What does it do? Well, it goes over to the ith slot. If this were 3, if I was 3, it would go over to this slot, and it increases the occupation number by 1 unit, but only for the particular I that we wrote down here. So if we go to the 7th oscillator and we apply the creation operator, it increases the 7th oscillator level. It does not increase the 6th one, it doesn't increase the 5th one. You know, there's an oscillator over there, it's over there. It's not to be confused with anybody else. And so, what this does is it leaves all the other ones alone. Let's say I is out here somewhere, and 1 and 2, dot, 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 until we get up to the ith place, and then it gives us ni plus 1, and then beyond that, nothing. But this is not quite right. This is not quite right because it fails to take into account the square root of n plus 1. So, what we actually have to write, what am I writing? I'm writing nonsense. Ni equals n1 dot 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 ni plus 1 dot dot dot. But we have to put in the square root of ni plus 1. So in other words, it works exactly the same as a single oscillator, with all the other ones just being bystanders, which play no role when you hit it with the ith oscillator. If you hit it with the jth oscillator, some other occupation number would get increased. Likewise for the lowering operators or the annihilation operators, same kind of understanding. So as I said, that's what we need to know about oscillators. Now we're going to come to quantum fields, real, genuine quantum fields, but in a very simple context. Non-relativistic quantum mechanics, ordinary quantum mechanics. Not relativity yet. We're not doing special relativity, just ordinary quantum mechanics. In ordinary quantum mechanics, there's some kind of funny connection between particles and fields. Particles are described by wave functions. Wave functions are functions of position. They sort of look like fields. What are fields? Fields are things, degrees of freedom, which depend on position and on time in particular. But let's just say position for the moment. Let's freeze time. Fields are functions of position. The wave function of a particle is a function of position. So you might think that's all there is to it. That's the connection between particles and fields. But it's not. It's not. For me, or at least it's only a very tiny part of it. And in fact, not the real idea. Right, okay. Psi of x. Psi of x is the wave function of one particle where x is the position of that particle. X could stand for x, y, and z, of course. It doesn't necessarily stand for just x. But psi is a function of x. But what is it? It's not an observable quantity. It's the state vector. It's the state vector in the position representation. It's not an observable. You don't do experiments to measure the wave function of a particle. You do experiments to measure the position of a particle, or the momentum of a particle, or the angular momentum of a particle, but not the state of a particle. You don't measure, that's not a measurable thing. It's a thing which tells you a great deal about the probabilities of various measurements, but it itself is not an observable. So that's the first thing, not an observable. Next fact, if we have several particles, then psi is not a function of one position, it's a function of all the positions. I want to exaggerate a notation a little bit. I want to make this a small psi, a lowercase psi. And it's a wave function. If I have two particles, let's call them x and y, again, not the x coordinate and the y coordinate of space, but just the coordinates of two particles, then the wave function is a function of two positions. Right. Function of several positions. In fact, it's a function of the position of all particles. Third fact, what was the third fact? Third fact is given a wave function which may depend on x1 through some number, whatever, x15. 15 particles. It's the description of a fixed number of particles. We describe 15 particles with a 15-particle wave function. Fixed number of particles. That is not the idea of a quantum field. By contrast, now, I'll tell you by contrast what a quantum field is, and in many respects it's everything that this is not, although we tend to use the same notation for it and it's closely related. Okay. First of all, a quantum field, these are wave functions, and they represent state vectors. Capital psi is different. Number one, it's an observable. It's a thing you can measure. Let's just think for a moment. What is a quantum field really going to be when we get to the real thing, real quantum, more complicated, serious quantum field theory? It's going to be things like the electromagnetic field. It's going to be the quantum mechanical electromagnetic field. The electromagnetic field is most certainly an observable. We observe it. And so, first of all, whatever psi is, it is an observable. Number two, psi is a function of only one coordinate. Oh, incidentally, the fact that it's an observable means that it's an operator. It means that it's an operator in the space of states. It's not itself a state. It is a operator. That must be if it's going to be an observable. Number two, it's a function of only one coordinate. Of one position. Function of one free vector, so to speak. And finally, it describes systems of any number of particles. Any number of particles. In other words, it's capable of describing systems where particle numbers can change even. Where particle numbers can change. How can particle numbers change? Well, if we were thinking about the electromagnetic field, and we remember that electromagnetic field is photons, every time electromagnetic field is radiated, it changes the number of photons. So whatever psi is, it's a description, it's an observable, it's an operator, it's a function of one position, and it represents the quantum mechanics of any number of particles, not a fixed number of particles. That's number one. Well, I don't want to go too fast because this is tricky stuff. Yeah.
X, where X can vary.
X can vary. Yes, X can vary, but it's a function of only one X, oh boy. It's a function of only one X, but that doesn't mean it's a function of X when X is 5. It means it's a function of X. X can be anything, but it's not a function of X1, X2, and X3. Okay. I keep telling you, why does... I mean, why... It's just a function of one coordinate. One coordinate in real world means 3 coordinates. It means X, Y, and Z. No, that's not what that Y is. That Y, 2 particles. One is named X, the other is named Y. Why? Because who's on first? That's why.
Psi X, Y. You got 15 particles in psi X.
Yeah, that's right.
Okay.
Right. Y is just X2. X is X1. Right. And 1 and 2 labeled 2 different particles. Right. We're going to do that. That's the whole point. I laid out for you the big contrast, and now we want to know what's the connection between them. And it's going to take a little while, but it's not... No, same kind of particles. Same kind of particles. And in particular, bosons. We'll come to fermions later. Yes, this is the theory of bosons. Everything we're doing tonight will be bosons.